been asked to find the length of the square spiral, r equals theta squared, where theta is between 0 and the square root of 5. Well, this requires us to know an arc length formula here in polar coordinates. We derived this in class, but the trick is to treat our polar function as a parametric function, and then we can simplify the arc length formula we know in parametric form to this. Well, I already know what r is, so I know what to do there. I need to know what dr d theta is so that I know what to substitute in here. So let's take a derivative. So it gets 2 theta. And so let's see. The bounds are given to me. Theta is between 0 and root 5. Not a typical angle to think about there at square root of 5 radians, but makes the problem kind of nice, honestly. R squared would be theta to the 4th power. Dr d theta squared would be 4 theta squared. And we're integrating with respect to theta. All right, well, we can simplify under that radical a little bit by factoring out a theta squared. Taking a square root will give us theta. Technically, I need to remember that that should be, or really is the absolute value of theta, but with theta being between 0 and root 5, everything is okay. All right, and now a d theta there on the end. Well, I think I know how to evaluate this using a substitution. I think we can let u equal theta squared plus 4. du is then 2 theta d theta. Just to help me out here, I'll just get d theta by itself. All right. I'm going to change my bounds. Plug in a 0 for theta, and u is at 4. Plug in that root 5, and we're going to get a 9. I have a theta for a second, u to the 1/2, and then du over 2 theta. Fortunately, the thetas cancel, and I have a 1/2 I can pull out front. All right, so I have that 1/2 I can pull out front. I'm integrating from 4 to 9, and then I have the square root. Well, I've already rewritten it using an exponent, so u to the 1/2 power, du. All right. Have that 1/2 hanging out front. U to the 3 over 2 times a 2/3. Evaluate from 4 to 9. All right, so let's see, that's really going to be a 1/3 where I multiply there, and then I have u to the 3/2 from 4 to 9. All right, plug in a 9, we get 3 to the 3rd is 27. I'll leave that 1/3 out front, even though 27 is definitely divisible by 3. Because when I plug in a 4, I'll get the square root of 4 is 2 to the 3rd is 8. On the inside there, I have 19 divided by 3 when I multiply by 1/3. 19/3. That's the length of this polar curve we were asked to find. Now, this one's not particularly bad, but sometimes when you're dealing with these arc length calculations, maybe we get an integrand that's not so easily simplified, and maybe we want to use our graphing calculators to approximate a length. So I'll put my graphing calculator back into function mode. And what I'm going to do next is type in the integrand as if it was an integrand with respect to x, because in a definite interval, well, the variable doesn't really matter. Next, I'm going to hit second calculate, and I want to find that value of the integral. Oh, I'm on a very odd viewing rectangle here, so I am going to exit out of that. I'm going to go to a standard viewing rectangle. I need to make sure x, the values of x here include everything between 0 and root 5. All right, so I still have my function entered in there, and so now I can go down. The lower limit is 0, and the upper limit is the square root of 5. And I get 6.333 repeating forever, which fortunately is 19 over 3, 6 1/3. So just in case we ever met a very ugly one of these, we could approximate it using our graphing calculators, just the way we have in class before. I wanted to show you what this curve looks like. It claims to be a spiral. And this is what this polar curve looks like if I graph it between 0 and the square root of 5. But I thought I'd really convince you that this is what we call a square spiral. So instead of just 0 to root 5, I'm going to expand the values of the parameter. And we see that it continues to spiral around, but it turns out even better than that. If I zoom out, I see that this is really a spiral that just keeps on going. So this is what the graph of that polar function looks like. Well, if t is greater than or equal to 0, just spiraling around the origin.